Okay, so we're going to look at this problem here and do some examples of circuit analysis with Laplace transforms before we get into transfer functions. Now, if we look at this one here, I should probably also tell you here, all initial conditions are 0. So, and then of course you can kind of tell by the way the problem's labeled, find V out at t. That's what we're going to be looking for. Well, you can see we actually have a fairly basic circuit. This is just a parallel RLC circuit, and we have just a standard step function as its input here. So just like we've done any of our circuit analysis with Laplace transforms, we have to first do the Laplace transform on the circuit. So that would give me 5 over s for u at t. And then of course we have 5 ohms still just for the resistor, 2s for the inductor, and then 1 over 1/2 s, which would be the same as 2 over s for the capacitor. And now there's several ways you could look at this. Honestly, and this is what we'll look at in a future video here, you could just combine all of these things in parallel, because if you're looking for the voltage, we know the voltage of things in parallel is the same. So we could get an equivalent impedance, essentially, and that voltage would be the same, and then just multiply it by the 5 over s. But I'm going to go ahead and do a nodal analysis, just because that's what we're kind of used to being able to do here. So I've got a current coming in, and then 3 currents leaving. So my current coming in is of course 5 over s, and then I'd have V out over 5 plus V out over 2s plus V out over 2 over s. Now I'm going to be a little bit careful before I do anything here. I'm going to rewrite this expression here. 5 over s is equal to V out over 5. And be very careful of your 5's and s's, especially if you're doing an exam or something. My habit has been that I can sometimes get my 5 and s's confused because I'm being quick in writing things out. But this term here, when I have V out 2 over s, I could rewrite that as s times V out over 2. And then from here, we can see that it would be advantageous just to multiply here through by 10s. So if I multiply through by 10s, I would have, well, the s's would cancel. I have 5, so that'd give me 50 is equal to 2s, because the 5 would cancel there. And then I have a 2s, times V out, of course. And then I have a 10s divided by 2, which is 5, and divided by the s, which gets me, so this would be plus 5 V out, plus, and then what do I have here? I'd have a 10s times a 10s times an s over 2, so that would be 5s squared times V out. And of course that gets me here 50 is equal to 5s squared plus 2s plus 5 times V out. And so we get V out is equal to 50 divided by 5s squared plus 2s plus 5. Now, what I'm going to do here is I'm going to actually rewrite this a little bit. You might find it a little odd the way I'm going to rewrite it here in a second, but I don't like having this 5 in front of the s squared, because if I'm factoring, I like to have that just not there. So I'm going to factor out that 5. And so I'm going to have a 50 over 5, and then it would be s squared plus 2 over 5s plus 1. And then of course I could cancel that and get a 10 up here. And this is 10 over s squared plus 2 over 5 times s plus 1. And of course we have to still do partial fraction expansion and everything on this, because if I pull up my Laplace transform table here, we can see that it doesn't actually have anything useful here. It's not in the form s plus a, and it's not s squared plus omega squared, and it's not this s plus a plus omega squared kind of thing. So we need to go ahead and factor this. And so this thing does not factor as is, so we're going to have to do complete the square. And to remind you how you do complete the square, yet again, we've talked about this once before, you look at b over 2 squared, which would be 2 over 2 times 5 squared, which would be 1 over 25. And so what we would write this as is that V out is 10 over, and then the whole point of doing this is we look at what b over 2 is. b over 2 is 1/5, so we'd have s plus 1/5 quantity squared. Well, here, let me write it out in more detail here. S squared plus 2/5 s plus 1 over 25. I'll put that in parentheses, but then I'd be left with 24 over 25. And so that means that V out becomes 10 over s plus 1/5 squared plus 24 over 25. Which actually means we're in a pretty good spot here. And you might not say it is first, but let's look at the the Laplace table again here. So we look at the Laplace transform. We're in this form where I have omega over s plus omega squared. And you might not think I'm in that form, but I absolutely am in that form. We have to do a tiny bit of work to get to that form here, but we can clearly see here, so I'm claiming that we have omega over s plus a squared plus omega squared. I'm claiming we're in this form, and we are, but we have a little bit of work we have to do. First off, what's the work we have to do? Omega squared is equal to just spaced out for a second, 24 over 25. That's just what it is. But I can do that. Find out what omega is. It's just the square root of 24 over 25, which we can again approximate what that is. And using my awesome Windows calculator, 24 divided by 25, square root of that, so 0.9797, so we'll say 0.9798. Okay, but you might say I have a 10 on the numerator. So, again, we can force that. So we want we want omega to be in the numerator. So we want some constant k times 0.9798 to equal 10, because that's what we have. So, well, then that's what we're going to do. 10 divided by 0.9798, which is 10.21. So k is 10.21. So then let's rewrite this. So V out is equal to 10.21 times, I'm going to put it in brackets now, 0.9798 over s plus a fifth quantity squared plus 24 over 25. Let's make sure that's a 9 there. But I'm going to slide it out here, but I just want to emphasize that's exactly this form, because we know that omega squared is 24 over 25. We found what omega was, 0.9798. So we have it in the proper form. We said, okay, well I have a 10 up here. Well, I need some constant k times 0.9798 to equal 10, because this is the omega that I need. So I figured what this constant k needs to be out in front. And so then we get for V out at t to equal 10.21 times, I'm just going to not do the inverse Laplace transform here, e to the negative 1/5 t sine of 0.9798 t volts. So we do get an answer here. There's not really too much work, just a little bit of work that we had to do manipulating here. Now, just as a side note here, this kind of problem would be a perfect kind of problem to put on an exam. A very quick problem, quite frankly. I know it took like 12 minutes to do it here, but once you get used to it, it's a very quick problem to do. There's not very much, there's really no partial fraction expansion we have to do. We just have to do like a complete the square or something of that nature. Maybe we would have to do a partial fraction expansion. If you'd have to do a partial fraction expansion, you'll know right away, because when you're at this step here, if you were going to have to do a partial fraction expansion, this would be something like s squared plus 3s plus 2, which clearly factors to s plus 2 times s plus 1. Then you'd have to do a partial fraction expansion. But again, that's an easy one to do. Here, though, we have to complete the square. Okay, not awesome, but not difficult. All right, so we'll look at some other examples here in a second, but I want to show you one thing that could have happened here that could be different. Is if we had, for instance, an initial condition on one of these devices, you might think that's awful, but it really wouldn't be that bad, because what we'd have here is the initial condition. For instance, if we had an initial condition on the inductor, well, if we have an initial condition on the inductor, what we can do is we could draw the initial condition in as a current source. And now this current source would have a value of this. I don't remember the formula off the top of my head, but we'd have some value here, and it would be a number. Whoops, I erased that. It wouldn't be a variable, it would be a number. And so that's now just another current leaving the node. And so that would just be another term right here. And then it wouldn't have V out with it, so we would just subtract it to this side and still do the whole expand everything out, multiply things, combine fractions, all of that big deal. So it really wouldn't be the end of the world.